Swayam Prabha. Digital India. Educated India.
Okay. Now we are going to discuss the conjugate gradient, rather it is called it as Fletcher Reeves. Let us start with algorithm. Most of them is a iterative procedure. This is also a iterative procedure of Fletcher Reeves method can be stated as follows. So, start with an arbitrary initial point x1 and set the first search direction S1 equal to minus delta of f of x1, rather we can write it is minus delta f1. Find the point x2 according to the relation x2 equal to x1 plus lambda 1 s1. Find lambda fi such that lambda delta fi equal to delta of f of x1 or xi, and set I si equal to minus delta fi plus modulus of delta fi square divided by modulus of delta fi minus 1 square into si minus 1. So, it seems to be it is a Newton method, and further Newton search method also follows. So, keep it in mind of the Newton methods, and somewhat it is differ slightly with the help of the x2 equal to x1 plus delta 1 s1, and compute the optimum step length delta I in the direction of si, and find the new point xi suffix I plus 1 equal to xi plus lambda I si, and test the optimality of the point of x suffix I plus 1. If x suffix I plus 1 is optimum, stop the process, otherwise set the values of I equal to I plus 1 and go to the step 4. So, this is the up to 6th step. Followed with that examples. Let us start with the function f of x1 comma x2 equal to x1 minus x2 plus 2 x1 square plus 2 x1 x2 plus x2 square. Now, the initial point is also given, the point is x1 equal to 0 0. Now, what you have to do? You have to find first delta f. So, delta f is nothing but formula is dou f by dou x1, dou f by dou x2. You know the function, it is called it as equation number 1, and partially differentiate with respect to x1. If you differentiate x1, it becomes 0, it becomes 1. If you differentiate x2, it becomes 0, therefore no need to write. If you differentiate with respect to x1, it becomes 4x1. It differentiate with respect to x1, 2x2, and differentiate partially with respect to x1, it becomes 0. So, this is the expansion of the given function in terms of dou f by dou x1. Similarly, you go to x2, that is dou f by dou x2 is partially with respect to x2 of the equation 1. So, that it becomes 0 and it becomes minus 1 and it becomes 0, and partially with respect to x2 it becomes 2x1, partially with respect to x2 is 2x2. I hope you can understand how to partially do with the multiple valued function. And then del f1 equal to at x1 x2 equal to 0. So, here these steps put x1 equal to 0 and x2 equal to 0, therefore, these two become 0, 1 only will come. Here also these two become 0, then minus 1 will come. Now, the rule is S1 equal to minus del F1. So, what we have got it earlier is a corresponding minus del F1 multiply with the minus. So, first one is positive, therefore, minus 1, second one is minus of minus plus 1. The rule is x2 equal to x1 plus delta 1 x1. x1 already we found out, that is given question, therefore, substitute here, and lambda is keep as it is, and then S1 we found out, you substitute it. then simply multiply with the lambda 1 of second matrix, so that it become minus lambda 1, add them minus lambda 1 plus lambda 1. So, this is the simplification of x2. Now, keep it in mind, let us go with x1 plus lambda s1 into minus x1. So, that you have to multiply this given equation, you get it. So, minus 2 lambda 1 plus lambda 1 square. Now, you partially with respect to lambda 1. So, it become minus 2, it becomes 2 lambda 1 which is equal to 0. Therefore, solve them, lambda 1 equal to 2 lambda 1 equal to 2 get cancelled, therefore, lambda 1 equal to 1. Similarly, you go to x2 equal to x1 plus lambda 1 s1, x1 you know 0 initial, lambda 1 just now we found that it become 1, and then s1 already found at minus 1 to 1, and multiply with them, the answer is minus 1 comma 1 for x2. So, once you got x2, go to the next iteration, delta f2 at minus 1 comma 1. The same procedure you have to do dou f by dou x1, dou f by dou x2 at minus 1 comma 1. Then we have minus 1 comma 1, and S2 is a formula corresponding to minus delta f2 plus modulus of delta f2 whole square by see this is delta f2, right, this is delta f2 delta f1 the square into s1. So, delta f1 square modulus is you already got it f1, simply taking the individual square minus 1 square plus minus 1 the whole square, because these two values got it, therefore, the value is 2. Similarly, delta f1 already we found out, that is also 1 comma minus 1, therefore, 1 square minus 1 the whole square is 2. So, now you substitute here, delta f2 is nothing but minus 1 comma minus 1, this is this value, and the two values we got it, that delta modulus of delta f2 square is 2 and modulus of delta f1 square is 2, substitute here, therefore, 2 by 2, and then s1 is already we got it minus 1 comma 1. Now, you simplify the matrix, it becomes minus multiply 1 comma 1 and 2 by 2 is 1 and minus 1 comma 1, add them 0 comma 2. So, we can proceed to x3 equal to x2 plus lambda 2 into s2. So, x2 already got it minus 1 comma 1. So, this substitute, lambda 2 we do not know, and s2 we just now got it 0 comma 2, substitute it. So, that for first expression is minus 1, for second row first column is 1 plus 2 lambda 2. So, once you got x3, then based on this we have to find out lambda 2. So, f of x2 plus lambda 2 into s2 is nothing but in the given function x2 you know, s2 also we just now got it, lambda 2 keep as it is, substitute it, you have a equation minus 1 minus 2 lambda 2 plus twice of 1 into 1 plus 2 lambda 2 plus 1 plus 2 into lambda 2 whole square. Now, these add minus 1 minus 2, this one keep as it is, here 2 keep as it is, twice of, multiply them, minus 1 minus 2 lambda 2 will come, here a plus b the whole square, a square plus 4 lambda 2 square plus 1 will come. So, what happened? Minus 2 and plus 2 get cancelled, these two get cancelled, and then minus 2 lambda 2 and 1 plus 1 is 2 here. So, this minus 2 you here, and then multiply with 2. So, it become minus 2 plus minus 4 lambda 2, and the last one is 1 plus 4 lambda 2 into plus 4 lambda 2. So, simplify and these two get cancelled, remaining minus 2 lambda 2 minus 1 plus 4 lambda 2 square, and we have a derivatives at that point, the gradient dou f by dou x2 equal to 0. Therefore, minus 2 plus x2 lambda equal to 0, therefore, lambda 2 equal to 1 by 4. Now we have a x3 equal to x2 plus lambda 2 s2, and x2 is minus 1 comma 1, and lambda 2 is 1 by 4, s2 you value 0 comma 2 you know, substitute here. So, corresponding entry add them, then it become minus 1 comma 1.5. Now you go to iteration 3, if lambda f3 equal to corresponding dou f by dou x lambda dou x1, dou f by dou f3 by dou x2, at x1 equal to minus 1 comma 1.5 substitute it, so that we have 0 0. So, S3 equal to minus lambda f3 plus del f2 by f3 by del f2 into S2. As usual, we have to calculate del f3 already for no, and this one is 0 and this one is 2, and S2 is already found out 0 0. So, net value is 0. If 0 comes, then the function reached optimum, therefore, x3 is optimum. So, this is the meaning of the problem. Indicate the member of the one dimensional step required for the minimization of the function f equal to x1 square plus x2 square minus 2x1 minus 4x2 plus 5. According to the Fletcher Reeves method, del f equal to dou f by dou x1. So, differentiate 1 partially with respect to x1, therefore, 2x1 minus 2 will come. Second one partially with respect to x2, so 2x2 minus 4 will come. Now, at 0 0 it become minus 2 comma minus 4, therefore, S1 equal to minus del f1. So, minus del f1 mean corresponding this value is 2 comma 4. Now, x2 the rule is x1 plus lambda 1 x1, x1 is 0 0 already found out, lambda 1 we do not know, s1 we found out 2 comma 4, and substitute it and simplify, you have 2 lambda 1, 4 lambda 1. Therefore, f of x1 plus lambda 1 s1 is equal to 4 lambda 1 square plus 6 lambda 1 square minus 4 lambda 1 minus 6 lambda plus 5 will come. Simplify, it become what? This become 20 lambda 1 square, and this add minus 20 lambda 1 plus 5. Now, the rule is dou f by dou lambda 1 equal to 0. Therefore, what partially with respect to lambda 1 of the above, 20 into 2 is 40 lambda 1, with respect to lambda 1 minus 20, and then with respect to lambda 1 of 5 is 0, therefore, equal to 0. From this lambda 1 equal to 20 by 40, which is equal to 1 by 2 equal to 0.5. Therefore, x2 equal to x1 plus lambda 1 s1, x1 already we got it, lambda 1 is 0.5 and s1 equal to 2 comma 4. Simplify, we have 1 comma 2 is a solution of x2. Since they are positive, further we have to go to x3. So, del f2 equal to dou f2 by dou x1, dou f2 by dou x2, we have 0 0. Now, S2 equal to minus del f2 plus modulus of del f2 square by modulus of del f1 square into S1. Del f2 is 0, therefore, minus of 0 0, and this value is 0 and this value is 20, for 0 by 20, and S1 is 2 comma 4, and simplify 0 into anything, this is totally 0, 0 into anything is 0, net value is 0, therefore, x2 reached optimum. Now, we are going to discuss Cauchy-Newton method. So, basic equation used to development of the method can be expressed as del of f of xi equal to minus ji into x minus xi equal to 0, or x equal to xi minus ji the whole inverse of del f of xi, call it as 2. Now, this can be rewritten as I plus 1 equal to xi minus j inverse of delta f of xi, because more general with iteration process I equal to 1, 2, 3 and so on. Therefore, more generalization of xi plus 1 equal to this. Now, note that the Hessian matrix is composed of the partial derivatives of f and varies with the design vector of non-quadratic objective function f. So, the basic idea behind the quasi-Newton or variable methods is approximate either Ji by another matrix or Ji inverse by another matrix of Bi using only the first derivatives of f. If Ji inverse is approximated by Bi, so this can be expressed as x suffix I plus 1 equal to xi minus lambda I star of Bi into delta of f of xi. Now, where delta I star can be considered as the optimal step length, so the direction Si equal to minus Bi into delta of f of xi. So, the computation of Bi is to implement the equation 4 and approximate inverse. So, the Hessian matrix Bi equal to Ai inverse is to computed, and for the first expansion of the gradient of f about an arbitrary reference point x naught using the Taylor series as delta f of x equal to delta f of x naught plus j naught of x minus x naught plus and so on going on. We restricted to approximation, though first two derivatives you have to take it. So, that equation 6 reduced. So, if we pick up 2 points xi and xi plus 1 and use ai to the approximate of a j naught, equation 6 can be written as delta of fi plus 1 equal to delta of f of x naught plus ai into x suffix I plus 1 minus x naught. So, delta fi is nothing but delta of f of x naught plus ai into x minus xi minus x naught. From 8 and 7 subtracting, so that delta f of x naught get cancelled and ai of xi minus 1 minus x naught by minus xi minus x naught is xi plus 1 of xi. So, that becomes the distance di. Similarly, delta fi plus delta f suffix I plus 1 minus delta fi is gi. So, that is what we have written 10 and 11. So, the solution of equation 9 di can be written as di equal to bi into gi. So, di you know, gi you know, now substitute it, you can get di in terms of gi and multiply with bi. So, bi is ai inverse, which denotes an approximation to the inverse of the Hessian matrix J naught inverse, and it can be seen that equation 12 represents the system of n equations is n square unknown elements of the matrix Bi. Thus, if n is greater than 1, the choice of Bi is not unique and one would like to choose the Bi that is the closest to J naught of inverse in some sense, and numerous techniques have been suggested the literature for the computation of Bi as the iterative progress. A major concern is that in addition to satisfying the equation 12 to symmetry and positive definition of matrix Bi is to be maintained. That is, if Bi is symmetric and positive definite, Bi plus 1 must be remain the symmetric and positive definite. So, these are all the key pointers more important, check it out, and this Bi and Bi plus 1 or symmetry and positive definite are there, then only it works. Now, we have to go to the further analysis of general format of Cauchy-Newton method. If the function being minimized f of lambda is not available in the closed form or is difficult to differentiate the derivative f dash of lambda and f2 dash of lambda in the equation 5.65 can be approximated by finite difference formula, right. Therefore, f dash of lambda equal to f of lambda I plus delta lambda minus f of lambda I minus delta lambda by 2 delta lambda, and f2 dash of lambda I is equal to f of lambda I plus delta lambda minus 2 f of lambda I plus f of lambda I minus delta lambda by delta lambda square. So, here delta lambda is small step size. Therefore, the equation 67 and 68 into equation 65. So, that lambda suffix I plus 1 equal to lambda I minus f dash of lambda I, you know, substitute it here, and f2 dash of lambda I substitute here. So, that the 69 will come. So, that is the required value of lambda suffix I plus 1. So, the iterative process indicated by using the equation 69 is known as quasi-Newton method. So, the test the convergence of the iterative process, the following criterions can be found, and take the modulus on both sides. Therefore, modulus of f dash of lambda I plus 1 equal to modulus of f of lambda suffix I plus 1 plus lambda delta delta lambda minus f of lambda I plus 1 minus delta lambda by 2 delta lambda is always less than or equal to epsilon. There the central difference formula has been used to evaluating the derivative of f and epsilon in a small quantity. So, we have a note. So, the central difference formula have been used in the equation 69 and 70. Therefore, the forward and backward difference formula can also be used this purpose. Therefore, 69 requires the evaluation of function at the point delta I plus lambda delta, sorry delta lambda, and lambda I minus delta lambda is an addition to lambda in each iteration. Now, we are going to discuss one problem. Find the minimum of the function f of lambda equal to 0.65 minus 0.75 by 1 plus lambda square minus 0.65 lambda into tan inverse of 1 by lambda using quasi-Newton method with the starting point lambda 1 equal to 0.1 and the step size delta lambda equal to 0.01 in the central difference formula. Use epsilon equal to 0.01 in equation 70 for checking the convergence. So, the method is here lambda is equal to 0.1 is given and delta lambda is also 0.01 is given, epsilon equal to 0.01 is also given. Now, you have to find out f1. f1 means you put f of lambda 1. So, you take lambda 1 lambda is equal to 0.1, substitute in the f of given function 1. So, that the net value equal to minus 0.188197 will come. Now, we have to calculate the first iteration f of 1 plus mean f of lambda 1 plus delta lambda. Lambda 1 is nothing but 0.01, delta lambda is 0.01, lambda 1 is 0.1, delta lambda is 0.01, and then you put it in the given function equation 1. So, that the net value is equal to minus 0.195512 will come, and for f1 minus mean negative that is f of lambda 1 minus delta lambda. So, lambda 1 is 0.1 and then delta lambda is equal to 0.01, subtract it, you can get the value. Now, you got lambda 1 and epsilon and so on. Now, the formula is for the quasi-Newton method is lambda 2 equal to lambda 1 minus delta lambda into f1 plus minus f1 minus divided by 2 into f1 minus 2 f1 plus f1 equal to, you substitute all the values here. So, that we get 0.377882. Now, we have to check the convergency. So, the rule is modulus of f dash of lambda 2 equal to, lambda 2, that lambda 2 is substituted in the f dash means differentiate partially with respect to equation 1. instead of doing that one, you calculate F2. So, F2 is equal to what? This lambda 2 is substitute, and F2 minus is also you substitute lambda 2 of the given function in terms of the negative, that is lambda 2 minus delta lambda 2. So, that the value of F2 plus and F2 minus can get it, divided by 2 delta lambda. So, delta lambda is 0.01, and you substitute here, it becomes 0.137300, which is positive, which is greater than epsilon. So, we have to go to the next step. F2 equal to f of lambda 2. So, f of lambda 2 is equal to, already we found out lambda 2, substitute in equation 1, we have minus 0.303368 will come. F2 plus stands for f of lambda 2 plus delta lambda. So, lambda 2 got it already, and then add with 0.01, you have what? Minus 3033 plus 0.01, and substitute in equation 1, we have minus 0.304662 will come. Now, you take F2 dash. F2 dash is nothing but f of lambda 2 minus delta lambda, and you know the delta lambda is 0.01, lambda 2 is 0.377882, you have the value, right. So, 0.377882 minus 0. Delta lambda is 0.01. So, you have 28876 and then 3 and then 0.0. This value substitute in 1. So, that 0.65 minus 0.75 divided by 1 plus this is call it as what? Lambda 2 minus delta lambda, substitute in the given instead of lambda, minus 0.65 lambda, this value substitute into tan inverse of 1 by this. So, the net value is minus 0.301916 comes. Now, you go to the lambda 3. So, lambda 3 is lambda 2 minus delta lambda into f2 minus f2 plus minus f2 minus by 2 f2 plus minus 2 f2 plus f2 negative. So, f2 you got it, and delta of lambda into f2 minus f2 dash also found out. Substitute the value, so that the resultant is 0.465390 will come. For the convergency, you take a modulus of f dash of lambda 3. The rule is f3 plus minus f3 minus divided by 2 delta lambda. So, f3 plus is nothing but f of lambda 3 plus delta lambda. f3 minus is f of lambda 3 minus delta lambda. Subtract them. Delta lambda is 0.01. So, that the net value is 0.017700, which is greater than epsilon. Therefore, it is not nearly equal to 0. Therefore, we have to proceed further. Then f3 equal to f of lambda 3, which is equal to 0.309885 will come, because lambda 3 already we got it, substitute in the given equation 1. So, f3 plus is equal to f of lambda 3 plus delta lambda. Now, lambda 3 is 0.465390, delta lambda is 0.01, this is already we given. So, that value here substitute equal to minus 0.310004. So, f3 minus equal to f of lambda 3 minus delta lambda, and lambda 3 is 0.465390 minus delta lambda is 0.01, and subtract them and find the value, you can get f of that value substitute in the given equation 1. So, that minus 0.309650 will come. Now, we have to find the value of lambda 4. So, lambda 4 is nothing but lambda 3 minus delta lambda into f3 minus divided by 2 into f3 plus minus 2 f3 plus f3 minus f3 you know, plus f3 minus also you know, and substitute in the equation. So, that lambda 3 is nothing but 0.465390 and subtract this value. So, that 0.480600 will come. For the convergency, you take modulus of f dash of lambda 4, which is equal to modulus of f of 4 plus minus f of 4 minus by 2 delta lambda, which is equal to 0.000350, and the value of the 3 decimal, which is also less than epsilon. Now, it is equivalent to 0, therefore, the process has converged. So, we have the optimum value lambda star equal to approximately equal to lambda 4 equal to 0.4080600. So, this is the solution of quasi Newton method of the function. Thank you.